Okay. So can you see my screen?
Yes, we have been using that slide, that set of slides, and we have been using
that set of slides. Okay, so but did you go to the description of counter in these slides? No.
No.
Okay, this is fine. Okay, so first of all, let me introduce myself, and I introduce myself using another set of slides from like similar but different slides, because in these slides I don't have introduction. So my name is Yuri Panchul. Uh, uh, Originally, I came from Soviet Union, so I was born in Ukraine and then studied in Russia. And 34 years ago, exactly 34 years, on August 12 of 1991, I came to California and started to work. And then I was working in software to design chips. Then I was working in design verification, and then I started to work in design. So I worked in companies MIPS Technologies, Imagination Technologies, Juniper Network, and right now I work in Samsung. So my job right now, I'm a design lead in a GPU, in a graphical processing unit, in a chip which is used, which is the main chip in a Samsung telephone. So we have like two kinds of Samsung telephone. One which is used Qualcomm chips, and another which is which use our oven chips. And like I'm working in our oven GPU, and my block I'm working in is a fixed function in a geometry subsystem. So which means that when you see like 3D computer games, like when you see like rooms and monsters and stuff, those all pictures are comprised of little colored triangles, and my hardware block get coordinates of that triangles in a floating point, and I like rotate them in space to put it into perspective, remove anything which does not fit the scene, and this is all done through hardware acceleration. And this works much faster than software on a regular CPU processor, because in hardware we can put many things in a parallel. We can process the whole stream of information. So before Samsung, I was working in Juniper Networks, and Juniper Networks is a company which is now part of Hewlett Packard, and it creates a router, so-called core router. It's like boxes which cost like several $1 million, and which are used to connect cities with internet. So you get like high bandwidth fiber optic cables, and then they all come to this router, and then from this router networking packets are routed to internet service providers and finally go to individual users. So I was doing design of a block for a chip in such router. And before Juniper, I was working in a MIPS, in a MIPS division of a British company, Imagination Technologies. Imagination Technologies is a company which created graphical processor in Apple iPhone, in first 4 Apple iPhones. And then like Apple started to do their own GPU, but using technology from Imagination. And MIPS, which was a division of Imagination I worked in, is known for designing MIPS processors. which are still used in many universities as a research CPUs. Also now many schools switched to RISC-V, but MIPS was a pioneer in a pipelining processor and in graphical workstations. Yeah, and before MIPS, I was working in the industry of electronic design automation, and I was a startup founder. So I created a startup which was called C-level design, and you can actually see it in Wikipedia. I will not go much about this. So wiki, yeah. So like I was a technical founder. Like let me share my screen. Yeah. So this is article in Wikipedia about C-level design. So this happened a long time ago, back in 90s. And I was a technical founder who wrote a tool for software tool to design chips, and we got funding from venture capitalists, from Sofinova Ventures, and from Intel Capital, and like our tool was used by Fujitsu, uh, Hitachi, and like other companies. So I also visited places like NASA Jet Propulsion Labs and show it to them. So finally, this was acquired by a large company called Synopsys. Yeah. So I believe like Jorge told me that many of you are interested in doing startups. So and you can certainly do startups in the area of chip design to make like design IP, to make tools that that do like various tasks in a design. And right now there are even like startups that are trying to use AI to design chips. And so today I spend a lot of time just mailing back and forth some like tasks, some problems for the startups to solve. So like AI is not good right now at solving design tasks. But even if it will be good in the future, in order to use it properly, you have to know the basics of how the thing works. And you can learn these basics only by doing exercises. So today is the day when you get the concept of sequential logic. And without knowing of this the sequential logic, you cannot even like figure out whether what like AI created for you is something useful or like total nonsense. Because like once startup sent me some videos, um, don't want to give me their code, and I clearly see this failing, and like there are some other things which are passing. So in order to judge, you need to know basics, and in order to train yourself on basics, you need to do exercises. So the exercises you do today, and like yesterday, today, and tomorrow is the basis for this knowledge. And in hardware design, one of first skill you need to have is to do exercises with sequential logic. So let me explain what sequential logic is. So let's get the very same slides. So first of all, what is the main idea of all hardware design? So this picture shows this main idea. You don't have to like understand it right away, but any piece of hardware, any like processor or even any like algorithm can be decomposed to two types of elements. One is uh, one is a combinational cloud. Yes, I have a lecture. So one is a combinational cloud, and another is a set of state elements, like a state register. So combinational cloud is just a lot of combinational gates, like AND, OR, XOR, multiplexers, and so on. And state registers, it's something that has like state or memory. So as you already discussed with Jorge, combinational logic is something you can like understand relatively easy. So this is just a formulas which have arguments like arguments A, B, C, D, and after some time, like after uh, like uh, uh, like 50 picosecond, this A, B, and C propagate through the circuit, and you get result in like outputs E and F. So in the combinational logic, the output is depend only on inputs. That like at any moment, if you put given inputs, you will get like well-defined output. And the group of such gates is called a combinational cloud. And you can use it to compute like either logic expressions or like arithmetic expressions. So, and the sequential logic is uh, logic which involved additional element, state element, or D flip-flop, and it essentially allow your circuit to be smart. So now, first, before we go to a sequential logic, the difference between hardware and programming is that hardware lives in a physical world. So when you change something in the input, you don't get output right away. So there is a delay. Once you start changing some inputs, the output don't get changed right away, but they started to change after so-called contamination delay. And for a while, the outputs will have some determined value. So they may get like 0 and 1, and then finally like stabilized on something. They may be even in a prohibited area where they're not 0, not 1, but something in the middle. And finally, after a time called propagation delay, your signal becomes stable. But how do you know when your signal is stable? Because with one technology and with like even like different temperature, this may get stable after like 50 picosecond or like after like 1 nanosecond. So in order to not to do any like guesswork, in order to have like stable and clean result, we are using a special reference signal called clock. And this reference signal makes computation deterministic, which means that whatever you do, you can expect the same result with same inputs if you take into account like clock cycles. So, and this signal called clock is has a certain period, and this period is must be chosen to be clearly more than the delay in your combinational logic. And actually, in the companies, usually first we choose first we like budget define clock frequency, and then we make the design to fit this frequency. So clock is a periodic signal which has a square waveform. So like it goes 0 to 1, 0 to 1. And the moment when it goes from 0 to 1 is called positive age. And the moment when it goes to 1 to 0 is called negative age. So this clock signal generator is coming from a little chip on your FPGA board. So you can find this chip if you look really carefully. So now you use clock together with a special element called D flip-flop. So D flip-flop is a minimal memory element. So this has two, in the minimal way, it has two inputs and one output. So D flip-flop stores 1 bit during 1 clock cycle. So during this 1 clock cycle, the value coming from D flip-flop is stable. So you can use it. So you know that this was value created in previous clock cycle, and during this clock cycle, it will be the same. So D flip-flop records the value of input D at the moment when clock changes from 0 to 1. And output Q is connected to this recorded state. So before we move further, let me demonstrate clock and D flip-flop on a FPGA board. So now what we do is we run VS Code. So we run VS Code, just a moment. Just a second, I need to connect something. Yeah, just a second. So this is, yeah, I need to probably put it in different way. So first let me get exercise. So yes, Jorge, so did you use exercise in a hackathon or did you use something else?
Yes, we used that once.
Yes. Okay, good. So now if you go to like hackathon, like is the problems or solutions, if you go to D flip-flop, so let's go to D flip-flop. Yeah, so yeah, so if you look to this example, you can see a code. Let me make this code larger. Yeah. So can you see this code well? Jorge?
Yes, we can see that on the Visual Studio.
Okay, so here is the code which defined flip-flop. So we will use a signal called slow clock, which is artificially created signal with a frequency of 1 hertz. So here we have a signal clock with a frequency of 27 megahertz, and then we have slow clock with a frequency of 1 hertz, and we have a reset signal. So now what we do is we create a wire called any key, which uses unary OR operation to get a signal from any pressed keys. So basically any key, which means that any key we pressed, it becomes 1. Now we connect wire D to this any key, and we have wire Q, and we connect this Q to LED 0. So here is a code for a flip-flop. This means always FF at positive H slow clock means that every time slow clock goes from 0 to 1, if you see reset, your D flip-flop gets set into 0, and otherwise you get value from the input and store it inside D flip-flop. So when we run the synthesis for this code, we can see the following. So let me now stop sharing and let me put everything on camera. Wait, I think I didn't connect it well. A second. Connects were different. Yeah, okay. So first of all, do you see this light blinking? This LED is connected straight to
Yes.
To the clock. So if you look back to the code, yeah. So let's just share this thing. So if you connect it back to the code, you can see that we connect LED 7 to slow clock. So this is our clock which runs with a frequency of 1 hertz, so 1 bit every second. Okay. Now look what happened when I press a button. So when I press a button, then so we have here like LED 0. Then like this LED 0 also get on, but it get on only at the moment if you press when clock goes from 0 to 1. Okay, so if you press very fast, okay, now it went. If you press very fast in the middle, so you see we press, then this will be ignored. So basically it's recorded only if you cross the threshold, and also if you unpress, it will not be turned off. So this also puts something into internal state. It memorizes value when clock crosses from 0 to 1. So now let's see why this is useful. So first of all, so let me share the screen again. Yeah, so now we can combine our combinational logic with D flip-flop. So before we actually go to counter, Jorge, did you explain how like adder works? Like anything about adders?
No, I mentioned about the book, and we have not been getting that.
let me tell you a couple of things about adders, because this is kind of useful to understand. Unfortunately, I didn't put adder to this set of exercise, and I should to do this. But let me show you some adder picture. Oh, I have actually adder in another set of exercises called book. So I'm right now working on a textbook with Purdue University in Indiana. So those are examples for this book. So you can see, in order to like add two numbers, you can use simply a plus operation. So can start with like adding two bits. So the minimal adder is like adder which just adds two bits and a carry in. So like if you add something by hands, like if you add binary numbers by hands, you probably already know how it works. Let's go to another example. 1 second. This was in labs events. Yeah, and initially we created this example for our seminar in Tijuana, but then I decided not to put it in another series of example, but I should probably put it back. So when you like add, let's say 4-bit numbers, you start from the right, you add like 0, and you have to, oh, this is actually incorrect. You need to put 0 and 0. So this will do carry. So you add first 0 and 0, and you get 0, and then you add 1 and 1, and you get 0, and you get carry, this +1. So this 1 goes to the next. And in order to build adder, so you can create adder just by using plus operation. So you can say that like we treat binary number from key 3 to key 3210 to key 7654 as two numbers, and we just add them. But we can also implement addition using logic operations. So if you want to add the two numbers, two 1-bit number, you just use AND and exclusive OR operation to generate a sum and carry. And basically, let me show you some slides I create for the book. Oh, actually, I have it in my presentation. 1 second. Yeah, so if you go to, yeah, so if you go to some slides which I now create for this textbook, so when you just work with simple gates, you can create logic operations, and you can also create multiplexer. So Jorge, did you go through multiplexers? So did you go through this type of code?
Yes, we went through the we run the multiplexer.
Yeah, so multiplexer is the element of choice. Yeah, just like with the multiplexer, if you want to implement addition, for example, if you want to implement this full carry, you can use inputs A, B, and you can use carry in, which is carry uh, the right, to generate a sum for these bits and carry out. And then you can put several such blocks and build a block which does addition. So now let me show how to build a block which does addition. Oh wait, did I share the screen? I think I didn't. Yeah. So yeah. So here is example how you can build addition using logic gates. You can simply use AND gates and XOR gates and OR gates to build a simple block which takes bits A, B, and carry in and generates sum and carry out. And then you can put a chain of such blocks. So let me find this picture of chain for it. Combination. 1 second. Just a moment. I need to find this picture. I will just so so now yeah so this is the picture. So you can simply put a sequence of such blocks into a chain and build a block which adds numbers. Yeah. So yes, Jorge. So is this kind of understood? So should I say like anything more about it?
Is understand? How you feel? Do you have questions about that? Or do you
Yeah.
want?
So, but the point is that you can simply get the AND or not XOR gates and build a circuit which implements adder. So what this circuit does is simply you put some binary numbers to an input, and after a certain number of picoseconds you will get output. So now let's get back to the counter example. So let's go through this example with a counter. So suppose in this block which has plus, you have a combinational adder, and in the block on the right you have two D flip-flops. So they together form a number from 0 to 3. So 0, 0 is 0, 0, 1 is 1, 1, 0 is 2, and 1, 1 is 3. Now, at this moment, these two flip-flops contain 0. So now we connect these two D flip-flops, which we call a register. We connect to this adder. So now 0 is coming from this register and is propagated to the input of adder. So when it enters input of adder, the output of adder is still undefined because the signal didn't propagate through this adder yet. So now what we are doing, we add 1 plus 0, and once we yeah, and once we propagate, for some reason this doesn't show it. Yeah. So we add 1 plus 0, but this 1 is not recorded into D flip-flop because we didn't get positive edge of clock yet. So now positive edge is coming, And when positive edge is coming to D flip-flops, we have a event called aperture. So this is like in photo camera. In a photo camera, there is aperture, which is the opening when you press a button of the photo camera. So this lets the signal in. So when positive edge is coming, it let one into counter. So now one is recorded inside those two D flip-flops. And now this one is propagated outside. Now this one travels to the input of adder, and then you do 1 + 1 equal 2, but this 2 is not entering register, is not entering D flip-flops. And then positive edge is coming again, and when it's entering flip-flop, we can record 2 into the register. So now 2 is recorded here. And then this 2 is coming out, and finally you can see that we compute every clock cycle based on a number which is stored inside the register. And this is the main idea in all digital hardware designs, that you combine combinational elements and registers, and you can create like many interesting circuits out of it. Okay, so Jorge, so is this understood? So do I need to like repeat anything?
How you feel it? ¿Qué tanto han entendido? ¿O están hechos bolas? Pregunte.
So let's if you don't like understand it now, you will understand it once you do exercise. So just try to do like a lot of exercise. So the first exercise we are going to do is yesterday you were running counter. So let's go back to the counter again. And let's get a binary counter code. Yeah. So here is a simple counter which is controlled by slow clock. So like as we said, there is a slow clock of 1 Hertz. And what this code does is that we use special signal called reset just to set a counter in 0. And we have a 32-bit counter. So from bit 31, 30, 29, 28, and so on, all the way to 0. And then we'll say that always when slow clock goes from 0 to 1, if we press reset, counter goes to 0. Otherwise, counter we get old value of counter from previous clock cycle and add 1 and put it into a counter for a new clock cycle. So in this construct, we connect past. So what we have here on the right is past, and what we have on the left is future. So we are saying that future is past plus 1. And then we put 8 lower bits of this counter to our LED. So now if we synthesize this design, let's open it in integrated terminal. Let's synthesize in this terminal, and then let's see what it does on the board. Yeah, so let me stop sharing. Yeah, so you can see, oh, maybe I should put it this way, because otherwise, yeah. So what you see on this board is that this is bit 0, this is bit 1, bit 2, bit 3, bit 4. So if you press any key, it does a reset. So let's press. Oh, wait, I need to press reset on the board because. Yeah, so you see that when it starts as 0, then it adds plus 1, then it adds 1, and it becomes a sequence of a binary number. So 0, 1, 1, 0, 1, 1, 1, 0, 0, and so on. So this is just doing counting in a binaries. Now, if you go back to the code, your question would be but usually when we design some real devices like a computer or like a telephone, we use much higher frequencies. So we use like gigahertz, like 1.5 gigahertz or more, or with some FPGA designs with this board we run 27 megahertz. So how to use this clock instead of this fast, this like a slow clock. So in order to do this, what we actually can do, if we try to use just a clock directly, and if you try to change, so if you try to change flip-flop just by using a regular clock. So if we, let's say, put here LED is equal counter 70, this will blink too fast and you will not see anything because clock is running too fast. So let's actually run clock right now and see what happens if you use just a regular clock instead of slow clock. Yeah, so you can see that this is all kind of blinking, and you don't really see what is going on. So if you want to see counting binary numbers without such blinking, one thing what you can do is you can see high bits of this like 32 bit counter. So instead of 70, you can see like 3124. So we can just check what bits of this number we can see. Yeah, so now you can see that it's now running running with a slow speed because we are looking only to higher bits of this 32-bit number. So if you put some like other numbers here, like if you put like 2316, then it will start to run faster. So let me share my screen again. So if you put, let's say, like 2316, and then if you synthesize, So you can see that it will now start to run faster. Yeah, so it all started to run faster. So basically, you can look to different bits of this counter, and if you use like low bits, it will change faster. If you look to the higher bits, it will change slower. And then once we have this thing, we can use it to create a design of a so-called clock enabler. And the reason I am showing it to you is we can use it for displaying something on a graphical screen. So now let's apply our knowledge to a graphical screen.
Okay, that's is where we have a different screens here that are big.
Just a second. So do you see? I will show you how to deal with a big screen. Okay, in just a moment. Let's actually. Well, you know what? One thing you can try to do. You can use labs not in a hackathon set, but you can use labs in a lab set, which has a configuration which is called. If you go here, like two graphics, and if you go to, let's say, rectangle, ellipse, parabola, what you can do is you can open it in integrated terminal, and then you can run a script called 06 choose another FPGA board. And what you can do here, it will show you a set of boards, right? And if you have larger screen, you can simply choose not 10 nano 9K LCD 480 272 TM1638, but instead you can choose 10 nano 9K LCD 800 480 TM1638. So you can choose board number 70. But you need to make sure that in a version you have, this is also board number 70. And once you choose this board, if you run this script, it will synthesize to a board with a larger screen. And in principle, I can try it right now, but I need to search for this screen in my boxes. But this is the way how you can work with a larger screen. You see, so you can try it. But let me go back to a smaller screen. But I can use the very same example. If you go back to hackathon, and if you go back to binary counter, let's actually modify this example to display something on the screen, right? So what you can do is that you can use some counter bit. You can use some counter bit to create a some like moving picture on the screen. So let's actually modify this counter example and create some new code in the runtime. So as you probably discussed yesterday, we have a graphics controller which gives you X and Y, right? And you need to produce color red, green, and blue, right? So if you want to draw a rectangle on the screen, all you do is that you create a block of combinational logic, like always comb begin, end, and then you put red is equal 0, blue is equal 0, and then green is equal 0, and then you put like if x is more than 50 and x is less than 100, or like you can simply put if x is more than 200, then red is equal 31. So 31 is the highest number in 5-bit channel. So this is the most red number. So if you do something like this, and if you synthesize it, what you see on the screen is you will see that part of the screen is going to become red, right? So let me synthesize it. I synthesized it in the wrong place. Let me go back to the binary counter. Let me synthesize it here.
The little dog.
Huh?
Nice little dog.
Yeah. Dog walking here. Yeah. So if you synthesize it, you can see that part of your screen became red, right? So basically, let me just show this on the screen, how this all look like. Let's get share. Let's get not a window, but let's see. This Zoom should have some whiteboard, right? So let me draw it on a whiteboard. Yeah. So basically, if this is your whole design, right? So this is the whole design on like FPGA on the board. And this whole design has a connection to a display controller. So in this display, there is a chip which controls to this display. And here you have some signals, but you as a user don't need to know about those signals. So you have several bits for red, for green, for blue, and then you have bits like vertical and horizontal sync. So here there is a module called a display controller, and here is your user block, which is called the hackathon top, right? So when you create some design here, you just get coordinates x and y coming from this controller x and y, right? And then you generate this red, green, and blue. So we need for each x and y to generate appropriate red, green, and blue, right? And when you write such code, which I demonstrated, so you're using so-called combinational always block, which means that this code just describe part of combinational cloud, right? So if you actually look to what this code does, so if you remove counter from here, so suppose you just comment out counter and just synthesize only this code alone, right? So let's go to Govin Logic Viewer, and let's see what kind of schematics you're going to get from this code. So there is a script called 05 run GUI for FPGA synthesis, and this script just runs a program, and you can go to schematic viewer, RTL design viewer, and you can see schematics for a circuit which is generated based on your code. So you need to find here hackathon top. So this is our module. Yes, so Jorge, is this visible? Can you make it larger? Yeah, so this is visible. Yeah, so you can see that this synthesis tool generated schematics which include a series of multiplexers. So this has a comparator, and this comparator is connected to like our X, which is coming from a graphics controller. And basically we are saying that if X is if this X is less than C8, so C8 is a hexadecimal number which is 50. Like I believe it was 200. Yeah, so C8 is 200. So if our X is less than 3, so in our code it's if X is more than 200, then it puts certain values on red channel. So then it goes to red channel, and then it puts all ones to this red channel, and it's doing it by using multiplexer blocks. So this is how a synthesis tool converts your code into schematics. So now if you put simple combinational logic, you are getting only combinational cloud. So if you go back to like our slides, we are essentially putting combinational logic same as here we have in this address. So if you go back to the slide, you can see that we are using combinational logic. So now let's connect state registers to it. And what we do is that we remove comments from the counter, right? And we know that in this counter, some bit, let's say bit 20 changes several times a second. So what we do is that we create a second counter called the counter 2. So let's call it the counter 2. And let's say that if counter so let's call it counter 2, and counter 2. So let's say that if the first counter bit number 20 is 1, so this is a bit like no, let's do something else. Let's say that if first counter from bits 20 to bit 0 is equal 0, so this counter increments every bit, it increments by 1, and it becomes 0 only several times a second. So if our original clock is 27 megahertz, so if our original clock is 27 megahertz, so this is 27 bits a second, and this bits 21 bits get overflown every 2 power 21. So 2 power 10 is equal 1024, right? So like 2 power 2, 2 by 2 by 2 is equal 8, but 2 by 2 by 2 10 times is equal 1024, which means that 2 power 20 is equal 1024 by 1024, approximately a million. So like approximately a million. So this means that if we have a 27 megahertz clock, which is 27 million bits a second, and if we divide it by 2 power 20, we are going to have like 27 times a second this bits will have a zero. So like every 27 times a second, this bits is equal 0. So now we can add 1 to this counter, which will happen like every 27 times a second. So let's do it. And then what we do is we simply change this expression, and we said that we put red only if x is more than 200 plus counter 2. Okay. So now, let me repeat it again. So we are using first block of code always at postage clock to make a variable which simply increments by 1 27 million times a second. And then we check its 21 bits. So we should actually put here 19 to 0. 19 to 0. And and the 27 times a second, we increment counter 2 by 1. And then we add this counter to our equation. So once we do this, let's see what we are getting on the screen. Yeah, so do you see me?
No.
Yeah. 1 second.
Okay.
Let me start it again. 1 moment. The problem is that this window got closed. So let me open it again. Just a second. Yeah, so do you see what is going on the screen?
Yeah.
So see, this red, this redness is moving. Okay, yeah, so now it moved outside of the screen. So basic idea is that we are using clock as a reference signal to increment the counter. 1 moment, I will run it again. What we can do in this code. So what we can do in this code, we can say that like if counter. So let's actually put that like if counter. Oh, I have to share screen again. Okay, so we can put here like a begin end, and we can put here like if counter 2 is more than like 400, then counter 2 is equal 100, else counter 2 is equal counter 2 plus 1. So this like counter will be increased by 1, the counter 2, every time 20 bits of first counter. Well, let's like in order to make it simple, let's not use bit slices, and let's just make this counter to be 20-bit counter. So this is just a 20-bit counter, okay? And let's make this counter just a 9-bit counter. So this is 20-bit counter, and this is a 9-bit counter. And let's say that if the first counter becomes 0, then second counter, if it goes beyond the screen, it should go back, let's say to 0. So this is 272, because this is size of our screen. And so like if it goes more than our screen, it goes back to 0, otherwise it's incremented by 1. And then we put equation for our combinational logic that if x is more than 200 plus counter 2, then red is equal, or we can simply put if x is, just a second, we zoom it, it doesn't work well. Yeah, so if x is more than counter 2, so let's make it even more simple. Then red is equal 31, right? So let's see the whole design again. So we create a 20-bit counter. And if we press reset button, this counter goes to 0. Otherwise, it increments on every bit, and which happens 27 million times a second. Then like every time this counter becomes 0, and this 0 happens 27 times a second, we check that if counter 2 is more than 472, which is size of our screen, it goes to 0, otherwise we increment it by 1. And then we put a combinational logic saying that if x coordinate of current pixel is more than our counter, we put it to red. So if you have such logic, we can make red moving up. You got some error. So we got red moving on the screen. So let's see what kind of error we got. We can also click on log.txt and see it in text from here, which is more convenient. So when you have error, you need to see error. Yeah, here's error message. So index 23 is out of range. Yeah, so we need to go back to this code. We can close this one. Yeah, so we are using here index 23. Yeah, we can comment this out because we are not using LED. So we can synthesize it. Now let me stop to share, and I will show you what we have on the screen. Yeah, you see that it's initially red, and then this redness is moving. Okay.
Yep.
Yeah, so now you can actually play with a Verilog syntax and you can do various things. For example, how to make the thing moving faster. So if you want to make the thing moving faster, and if you also want to move uh, green green color at the same time, so what you can do is you can you can create let's say a second counter which moves faster. So you can have two independent counters. So let's create like counter C3, and if reset we put counter C3 to 0, and then if counter C3 is oh sorry, this was actually a regular counter. So if you have a regular counter to 0, and if C3 is more than like 200, this was actually 272. The width of the screen was 480. 480, 272. Then you put C3. So let's actually increment not by 1, but let's increment by like, let's say 10. So we can increment it by 10. And then you put that if y is more than C3, is more than C3. Yeah, with this zoom, everything becomes slow. So let me close all unnecessary windows. Close. Okay, so now let's put that if y is more than C3, then green is equal 63, which is a maximum greenness. And let's make something interesting for blue. So for blue, we can put that if x multiply x plus y multiply y is less than 10,000, so then blue is equal 31. So by doing this, we will effectively draw a circle with a radius of 100. So now let's see what we are going to have on the screen. Yeah, so let me stop sharing and I will show you what is going on the screen. So let me. So do you see it? Yes, Jorge. So do you see this picture?
Yes, we see everything. Yeah.
So like you see now, if you want to make it even more fancy, you can create some like interesting patterns, and I suggest doing those exercises because uh, like by doing those exercises, you learn syntax of Verilog, and you can create visually interesting pictures. And there is even a competition called demo. What is the name of this competition? So when people draw some like pictures, and you can make a like sequential and combinational logic to make such moving pictures, and by doing this, you learn very well. And then, if you want to continue with this, you need study uh, to study more, to like learn about pipelining and about how processor is organized, and things like that. But you can start learning very lot by simply doing such exercises. So okay, now let's try something. Let's try something like other things. Let me share the screen. So now, what happens if we add if we assign um, to green like our coordinate x? So let's assign coordinate x. So this will just show now a pattern on the screen. Yeah, you see, so now like it shows the kind of patterns. And now, like once you learn how to do such moving objects, you can actually create a game. And uh, here is a simple example of a game where you have two moving objects. So I will show you how this game look like. Just a second. Yeah. So. Um, Yeah, so you see, in this game, you have like two objects, and then you use buttons to move one of these like objects, and if you don't hit, it becomes uh, yellow, and if you hit, it becomes red. You see, so what actually I did last March? So I'm going to different countries. So in March, like few months ago, I went not only to Tijuana, but I also went to a country of Armenia. And in Armenia, we had a hackathon. So I want to show you how this hackathon looked like. This is on our website, Verilog Meetup. So when we went to Armenia, so this is a country, one of countries of former Soviet Union, and uh, they like located in a Caucasian mountains, so near Iran and Turkish and Azerbaijan, and there were like students. First, they had like some conference, which was a conference on electronic design automation, sponsored by both US and Chinese companies. So this was kind of interesting conference because it was attended by US companies, Chinese companies, and Russian companies, which is like rare because of politics. But there were some people representing like large US company Synopsys and the European company Siemens and the Chinese Huawei, and they all did uh, such like presentations about the chip design and supercomputers. And then we created a hackathon, and we simply got like a bunch of students in a room, just like with you. So this is how like it looked like, and they got the very same boards. And then we went through code of this example game, and then like in next like couple of days they're working on their own games. So for example, uh, like this girl, yeah, yeah. So like this girl, she connected ultrasonic sensor to this game so that she was controlling it not by keys but using ultrasonic sensor. And there was another girl, and she connected microphone. Yeah, so she connected microphone, and then she was showing notes with this microphone. Yeah, and this girl, she got first prize. Yeah, so so she put the whole bunch of figures on this screen, and there were some like also people from a high school, and yeah, so we like organized this kind of hackathon there. So you can do it too. You have like more than enough time, so you can go through the code of this game, and the code is this in game example. So this is design which is like 250 lines long, so it's not that big, but you can start with the first simple graphics. Okay, well, yeah, and another thing I also did in country of Azerbaijan, which is country next to Armenia, and in that country we were studying how processor is organized, and this is another thing what you may want to do. So if you go to this seminar in this country, what we did, we uh, first first I show them how to use instruction set simulator to learn assembly language for RISC-V processor. And once they learn RISC-V assembly language, and they learn how to run a simulator, we created a literal processor and put it on the board. So you just instantiate a module with a processor and connect it with memory and load program in this memory, and you have a working processor. So we were using like different board, but with your board you can do same thing. And then we're running like showing how register inside processor changes, and then you can actually implement your own ASIC. So on a foundry. So the ASIC is a fixed chip which is made on a foundry, and what you do, you can use service called tiny tape out. So there is a service called the Tiny Tape Out, and you can use for like very small amount of money to just put your design on part of this chip and make your own chip. So in order to do this, you first can practice on FPGA board, and once you practice on FPGA board, you can you can use this template called Verilog template for Verilog meetup. Yeah, and you can put your hackathon top code inside here. So this is your like hackathon top code, and then you can use this infrastructure to make an order and to make a chip. So basically, you can test your design on this FPGA board, and you can test it in simulation, and then you can make your own chip, and you can make a processor chip. So yeah, now like I have a question. So how many? Let me put this thing back. So first, like a Jorge. So can you ask? So how many of you studied assembly language, or like any assembly language, like x86, ARM, or maybe RISC-V? So Jorge, can you ask?
¿Cuántos de ustedes estudiaron ensamblador? In the morning they say about 2 or 3 of them knew a little bit about that, but not too many.
Okay. Yeah, but actually studying assembly language is not very difficult. But like assembly language is the interface between software and the processor, like between software and hardware. So this is exactly like on the border between software and hardware. And you create a circuit, like you create this CPU, and CPU just gets instructions from memory written in assembly language, uh, and uh, you, when you have like high level language like C, C++, it all is compiled to assembly language, and if you want to go from very low into building processor, then you can learn both like software and hardware part. But right now, I recommend to concentrate on exercises with a very low sequential logic, combinational logic. So one thing what you can do is you can get a book by Harris and Harris, so you can get some tutorial in Spanish, and learn some so yeah, 1 second, I will show you one recommended book. Yeah, this is book by Harris and Harris, Digital Design and Computer Architecture. This is a useful book to learn. So Harris, Digital Design and Computer Architecture. Yeah, so I'm talking about this book. Yeah, and right now I'm writing together with a professor in Purdue another textbook, and by the way, he knows some Spanish, so maybe we can create a like eventually Spanish version of that book as well. Yeah, so this will
Are you sharing which is the book?
Oh, I have started to work on a book in a contract with the Purdue University. So this is uh, a school in Indiana.
Yeah. Okay. You are not.
So
you are not sharing your screen.
oh yeah. Let me share my screen. Yeah. Yeah, so we are now working to publish a textbook with this university, and since I'm originally from Soviet Union, from Russia and Ukraine, so like unfortunately they have war now, but my father is Ukrainian and mother is Russian, so sort of on both sides of this conflict. But in Russia, we created classes called chip design school of synthesis of digital circuits, and now it is used in like 20 something universities in Russia, and they, so like you can see here, like me as a founder of this school, yeah, and there
No está grabado, lo pueden ver 3 veces. This is one tutorial. This is one class. This was really fast. We lost you.
¿Le habrá mandado un mensaje por Telegram?
¿Mande?
¿Le habrá mandado un mensaje por Telegram?
Sí.
Yes, I'm sorry. I got I got briefly disconnected. Yeah. So now let's So most of it is exercises. So now just to give you some feel about how this hardware design looks like. So let's talk a little bit about how design is organized in a company. Okay. So first of all, I will show you like our office in San Jose. Yeah. So this like office in San Jose, California, where I'm doing this design. Yeah, so we have here like large office, and it's futuristic. Yeah. Yeah, so this is essentially our office. Yeah, so this is our office. You can just find it in Samsung San Jose office. And so we have team, and part of team is working in California, and part of team is working in Texas, and we working with team in South Korea. So we're doing like a graphical part, which is GPU, which is like Exynos GPU. So Exynos Samsung. Uh, yeah, so this Exynos mobile processor, and um, like we write code in Verilog, and then we use a simulation, and then we are using emulator, including FPGA based emulator, but like our FPGA boards we use uh, for for trying our designs before going to foundry, they are different. Like board you use, this is like student board, and it costs like 50 bucks. So like it's cost like small amount of money, but boards we use to test design on phones, it actually cost like hundreds of $1,000s, like even like $1 million. So there is like emulator called Zibu, which is used to test it. And when we run this emulator, so let me show you what kind of benchmarks we are running there. So one benchmark is called wildlife um, GPU benchmark. So let me just show you how some of those. Yeah, so this is called Wildlife Extreme, and this is kind of test we are running on this FPGA board emulator. Yeah, I know this video doesn't show this benchmark. It's actually really wild. 1 second. Yeah, this is wild. Yeah, this is a good video. Wildlife Extreme. Yeah, so this kind of like moving graphics, it's something we use for our testing. So each such picture consists of like tens of million color triangles, and because regular software cannot process them fast, like display this 3D worlds on the screen, we need to make a custom design, which is done in Verilog. So like I'm using the same like Verilog you're using now in your exercises, but for design which is much larger. So to make a GPU, yeah, you see, so this kind of monsters. Yes, Jorge, do you see it on the screen?
Yep. Yeah. We're seeing very
Okay, good.
well all the video.
With this kind of design, yeah, with this kind of design, and in order to make a telephone to display this kind of 3D image, so what you need to do is viewport transform. So you essentially specify, you use like that one. First you use like game engines, and then you use OpenGL or Vulkan, library, which is a software library, and you also can write in a special language which get compiled into something which is understood by this 3D graphics engine, and then goes through shaders, and then like I have to do in hardware floating point arithmetic to convert from this coordinates into perspective. So I cannot show you how like our code looks like, because this is proprietary code, but we are talking about like millions lines of code. And if you do some more exercises with our like open source library, which we with Jorge and with other people maintain, so you can go to like Verilog meetup GitHub, and we also have exercises. We also have exercises with floating point arithmetic, and if you look inside those exercises, they actually look in many ways similar to what we do in this GPU phone. So you can see here some like test bench code which is written in Verilog and which works with floating point numbers. So we are doing the same in commercial chip, but in commercial chip it's something much larger. So now there are like some AI companies which are trying to sell what they can do using AI, but right now AI is too weak to do this kind of design. So I'm sending them examples, and they're trying to do something with it. Yeah, so if you want to see some like next level exercises, once you learn the basics, you can go through this system Verilog homework, which has like bunch of this exercises with like um, floating point coprocessor, like 5 AQs and so on. But before doing this, uh, I recommend to get a solid idea on what you do with basic constructs, the constructs we just learned today. So you just need to do with small steps. So just go through every exercise and try maybe to create your oven liter game. Yeah, so we went through combinational logic, we went through multiplexers, and so next we went how to draw things on the screen, what is flip-flop, what is binary counter. We learned how to move things, and then uh, you can also see some examples how to use like ultrasonic distance sensor, which is also sequential design, and how to use rotary encoder, and how to connect this design to a microphone and to like a sound output. So because you have more time, I think Sebastian can show you how to connect uh, design to the microphone and make some like labs with the sound. Yeah. So did you show already how to make FPGA board to like understand sound?
Yeah, we has been talking about all the cycle, and we are the only thing we are not going to be using right now is the mic and the soundboard. We are not expecting to have the time. And on Thursday, a friend of mine that is doing the open lane construction, he already has done 5 boards. He's going to give us all the details how to convert that from the stage where we are into ASIC kind of things.
So you're talking about like open.
Open
You're
lane.
talking about uh, open lane seminar and with like as they use it, lattice board. You're talking about those people.
Okay, no, we're not using
Yeah.
lattice. We're using the
Huh?
the,
Ah,
the
okay.
9K
Yeah,
channel.
but that one cheap, like one of those companies was using. Yeah, but basically, you can start. You can either use open lane or you can start with a tiny tape out. But because you're using the same Verilog, first you practice on FPGA board and then you can convert it into ASIC and run everything. Like run everything in ASIC. Yeah.
Yep.
Okay.
It has been quite a bit of work.
Okay, so what else do you plan to do during this week, and what other topics do you want to discuss right now?
Well, tomorrow the big challenge is to be doing something with the LCD screens, try to write some things, play, generate some kind of dashboard or lines or graphs, whatever is possible to be done there. And that is going to be tomorrow. And on Wednesday, on Friday, Thursday, that is the last one, is mainly a recap of all the things. And they have already a 4 projects or 4 challenge, and they are trying to use it for how to do water system measurement or different. There are four different projects they are working, and they're looking how they can use the FPGA as a tool.
If you want to know more about applications of FPGA, so let me talk a little bit about this because this is kind of interesting subject. Yeah. So first of all, as you can see, there are like some fixed chips which are made on a with like fixed design made on foundry, and there is FPGA, and in order to implement the same schematics in FPGA like as an ASIC, you need to spend more transistors. For this reason, if you for instance, in our like phone chip, the chip inside the phone is small and it runs on very high clock frequency, on like gigahertz frequency, like application processor and like other pieces run in different frequencies, and it consumes relatively small amount of power, so you can live with a battery on a phone for the whole day or more. But if you try to do the same kind of schematics inside FPGA, then you need to use the whole box of FPGA, and it will run on like megahertz, like 10 or 20 megahertz frequency, so much slower, and it will be much more expensive. But uh, uh, so but in order to make such like 2 nanometer telephone chip, you need to spend like tens $1 million to just start production, and then so this is justifiable only when you sell like tens of millions phones, and each phone costs a lot, so you spend a lot of money and you get this chip. But if you want something right now, you don't have option to manufacture expensive ASIC, so you can use FPGA, and then you can compensate for the limitations of FPGA with a parallelism. So like if you get some microcontroller, so if you get let's say like Arduino or like Raspberry Pi or like other microcontroller, they run with like Arduino may run the same clock as FPGA, but because it does things sequentially, and in FPGA you can do things in parallel, you can start many things and run faster than a microcontroller. So for this reason, FPGAs are used in applications like a space company. So if you go to like Blue Origin, um, like Blue Origin FPGA jobs, let's see there whether they have anything. Okay, Blue, yeah, Blue Origin. Yeah, so you see, if you look for like companies which make like space rockets, so for instance, Blue Origin. So you can see that Blue Origin, they hire FPGA design engineers, and Blue Origin is a company which make rockets. So this is funded by Jeff Bezos. It's the same person who is a founder of Amazon. Yeah, so you can see his rocket here. Let me close this. Yeah, so you can just Google for Blue Origin, and so they are trying to make something for the moon, and they actually hire. So the reason they hire engineers for FPGA design is that because uh, you don't have many like rockets, you cannot make ASIC for a rocket, because to make ASIC on a foundry you need to spend a lot of money. Like commercial ASIC is like millions of dollars, and there are like only a few of rockets, so it's not practical to make a special ASIC. So what they do is that they use a network of microcontrollers and FPGAs. So many uh, they just connect many FPGAs and microcontrollers together, and then they use FPGA, like they call it input-output extender. So when you have some like sensor, so like rocket has many thousands of sensors. And like each sensor measures something, plus they also have GPS signal, plus they have actuators, so they need to move this rocket pins when like rocket is flying in space. And for this reason, microcontroller is not fast enough to process this data, so they put some processing in FPGA and some processing in a microcontroller. And because they can put in FPGA a lot of parallel processing, they make such mix of components and do their sensor uh, uh, processing tasks. Yeah, so this is one way of using FPGA. Then, like another way is educating of future ASIC designers. So this is what we are doing with you. And like another way, as I said, that there are FPGA based emulators. So there is a ZIBU emulator, which is box used by so this is like expensive board. So this is like such box. So this box cost I don't know, it's exactly price, but similar box from Siemens cost $6 million, and this one is less expensive, I think. So, but this is $700,000 for sure. So this box has many FPGAs inside, and like companies like Intel, before making Intel chip, um, they put their design in this Zibu emulator and they tested there. Like also in emulator, you cannot run design with same speed as Intel processor in your computer, but you can still run it fast enough for debug. So when you write something in Verilog, you so when you run something, when you write something in Verilog, you can simulate it in a program. So there are some software simulator, but with a software simulator, you can run CPU tests for like several thousand instructions. But if you want to, let's say, like boot Linux or boot like operating system on a processor which is not manufactured yet, you need to use emulator. So this is like another large area of using FPGAs. Yeah, and FPGAs are also used in some medical device with video processing and with like processing of signal from a telescope. So I know that, like, for instance, in country of Kazakhstan, on a Baikonur a spaceship place, they have like telescope and they were using FPGA board to get signal from the telescope because you can put it faster than you can do it in software. So, like, of course, it's slower than to make a custom ASIC, but to make custom ASIC on Foundry, you need to put order, wait for months, and this is expensive. But with FPGA, you can do it right away. So this is kind of general idea of how FPGAs are used. Yeah. So, Jorge, is it like informative?
I guess very much. They are overwhelming with that, too much information now. They need to digest.
Okay, yeah, sure. Okay, so do you have any other questions, any suggestions?
Questions?
Yeah. If you need,
Yeah.
yeah.
Yeah, one here.
The FPGA technology is already enough, but to emulate a processor like the CLB of the PlayStation 3.
I didn't get it. Is
Can
the
you?
FPGA technology
Is enough already to emulate a processor like the CLB of the PlayStation 3?
is with FPGA you can build any of the processors that you want.
Yeah, but
Yeah. I think I understand. With certainly, when you do place and route, when you need to place logical elements in ASIC and in FPGA, you have to do it in different way. Besides, in FPGA, there are limits on how many signals you can put from one FPGA to like another FPGA. Yeah, those are all limitations, but with FPGA, you can make cycle accurate design, which means that even its physical organization is different than in ASIC, but on every clock cycle, signals will have the same value function. I'm not sure whether it answers your question. Or like Jorge, can you ask to like? You can send me an email. I can send you email about it.
Yep.
Yeah.
Then they
So
already have
if
your
you have yeah, if you have any problems running any tools tomorrow, then you can simply try to reach me on like Telegram. I will answer right away. So tomorrow I will be in office, but I will look to the Telegram, and if something happen, or you can just call me, and if something happen, I can answer your question right away. And speaking of large screens, as I said. As I said, you can use a lab set of examples, or I can create a special version of a hackathon examples for a large screen. So if I create it, I can create it even today, and if it works, I will just send you message and you can test it.
All right. We appreciate very much your help. How do you think? Do you like it?
Okay, thank you. Okay.
Well,
Okay,
thank you very much. And
good night and more exercise, because here the main thing is to do many exercises, and by doing exercises you will learn more. If you only memorize book, you will not get it, because you see, I interview a lot of US students, and those students who do exercises, they do well on job interviews, but if they only memorize books, they don't do well. I give them questions they cannot solve. So if you want to go to like on job market well, or do some startup and present to VC, you need to develop skills by doing a lot of exercises. Yeah, so try to do a lot of exercises tomorrow and increase your proficiency. Yeah. Okay, so thank you.
well, thank you very much, and see you next week. Well, in 3 weeks, I'll be back there. I'm going to be the 2 weeks more here in Mexico.
Yeah, okay, so see you.
Bye now. Thank you very much.